Have you ever really stopped to wonder how your phone, your computer, all your digital gadgets, how they actually understand the world around us? The world of sound, light, temperature. Well, it's not magic. It's actually a translation, and it's happening millions of times a second, thanks to some incredible and pretty much invisible components. So let's pull back the curtain on these hidden translators. Okay, so at the very heart of this whole thing, there's a huge communication barrier. See, the physical world and our digital technology, they speak two completely different languages. And for them to talk to each other, you absolutely need a translator. So let's start with a really simple question that gets right to the point. When you talk into your phone, how does that physical vibration in the air, your voice, get understood by all the digital circuits packed inside? On one hand, you've got the real world. Think about things like the warmth of a room, the sound of your voice, or even physical pressure. These things are all continuous. They're infinitely variable. We call this analog. But on the other hand, you've got our digital devices, our phones, our computers, and they only understand precise, separate pieces of information. So here's the key difference. Analog signals are these smooth, continuous waves, kind of like using a dimmer switch on a light. You can have any brightness in between. Digital signals are the exact opposite. They're like a regular light switch. It is either on or off, a 1 or a 0. There is absolutely no in between. And here's the big problem with the analog world's language. Because it's a continuous wave, it's super sensitive to interference, or what we call noise. Any little bit of static or electrical disturbance can get mixed in and totally mess up the original signal. Just think of the static you hear on an old radio. But digital signals, they are way more robust. Since the system is just looking for a clear on or a clear off, it can easily ignore all those minor little wiggles from noise. And that's what makes digital information so much more reliable to store and send around. So how do we bridge this gap? How do we get the noisy, kind of messy analog world to talk cleanly with the super precise digital world? Well, we use two incredibly important devices that act as our translators. First up, we have the analog to digital converter, or ADC for short. Its entire job is to listen to that analog signal from the real world, like your voice hitting a microphone, and translate it into the only language a computer speaks, a series of numbers, or bits. And of course, we need to go the other way too. For that, we have the digital to analog converter, or DAC. A DAC takes that digital information, say a song stored as an MP3 file, and it translates it back into an analog wave that a speaker can actually use to make sound. And this right here shows the complete round trip perfectly. The ADC takes that smooth analog wave and chops it up into digital code. Then, the DAC takes that code and rebuilds the analog wave on the other side. They are the perfect team. But how? How does an ADC actually do that? How do you turn a smooth, continuous wave into a list of numbers? It's a really cool two-step process. So the whole thing breaks down into two main ideas you see here. First, there's sampling, which is all about when to measure the wave. And second, we have quantization, which decides what value to give each one of those measurements. Let's dig into each one. Sampling is pretty much what it sounds like. The ADC takes thousands, sometimes millions of tiny snapshots of the analog signal every single second. It measures the voltage of the wave at these super precise, regular moments in time. The faster it takes these samples, the more detailed a picture it gets of the original wave. Okay, next up is quantization. Now, for every single one of those little samples the ADC just took, it has to give it a number. Think of it like rounding a number up or down. It takes that super precise measurement and just finds the closest available number on a scale it already has defined. And this is where a really key concept comes in: resolution. You see, the number of levels the ADC has to choose from is called its bit depth. And it's simple, really. The more levels it has, the more accurately it can represent the original analog signal. Now, this is where you can really see the difference. On the left, a low-resolution 3-bit ADC has just a few levels to choose from, so its digital version is this rough, kind of blocky approximation. But look at the right. The 8-bit ADC has way more levels, which lets it capture the true shape of that wave with so much more accuracy. All right, so we've turned our wave into a super accurate series of numbers. Now, how do we turn it back into something we can actually hear or see? Well, that is the job of the DAC. A digital to analog converter basically just does the reverse of quantization. It reads each number in that digital stream, and for each one, it puts out a specific voltage level for just a tiny fraction of a second. By stringing all of these little voltage steps together, it rebuilds the analog wave. And just like with ADCs, resolution makes all the difference. I mean, look at that blue line from the 4-bit DAC. It's a clunky-looking staircase. But the red line from the 16-bit DAC, it's so much smoother, a much more faithful copy of the original signal. This, right here, is why music lovers care so much about the quality of the DAC in their stereo system. So we've gone through the theory, but why should you care about any of this? Well, the truth is, these little translators are absolutely everywhere, working silently in almost every single piece of modern tech you own. Let's go all the way back to our first question. When you talk into your phone, the microphone captures the analog sound wave of your voice. An ADC chip inside that phone instantly samples and quantizes it, turning it into digital data that can be beamed across the network. And when you listen to music, the exact same thing is happening, just in reverse. A digital file, like an MP3, is nothing more than a long stream of numbers. That data gets fed to a DAC, which rebuilds the analog sound wave and sends it to your headphones so you can actually hear it. And believe me, it doesn't stop there. CD and DVD players use DACs to turn the little pits on the disc into audio and video. Your digital thermostat uses an ADC to read the analog temperature of the room. Even things like printers and huge industrial machines rely on this constant translation between the digital and analog worlds. These converters really are the unsung heroes of our digital age. They are the essential bridge between our reality and our technology, which, leaves us with a pretty fascinating question. As our ability to sample and measure the world gets more and more precise, what's next? What other subtle analog parts of our experience will we soon be able to translate into the language of ones and zeros?